Hello everyone. In this video, I wanted to make a brief introduction into what are electric motors. In particular, in this video, I want to make a brief overview into what are the principles that to allow us to design and also control electric motors. Okay, how we can generate torque, no, produce some mechanical work based on these electric motors that basically converts the electrical energy into mechanical energy. Okay, but in order to understand how the electric motor does that, we need to first understand the physical principles that um, describe, no, the behavior of these electric motors and also their functionality. Okay. So the first law that we need to take into account is the Faraday's law. Okay, the Faraday's law is also known as the induction law. And basically, what the Faraday's law states is that let's say that you have, for example, a coil. No, we have here a conductor, and let's say that I have here a magnet. No, in this position. Okay, this is the north pole, and this is the south pole of the magnet. Okay. So when this magnet moves closer to the coil, okay, and I start moving or varying, or moving this magnet near this conductor, no, this is the conductor, I can induce a voltage in the conductor due to the presence of a varying magnetic field that is near the conductor. Okay? Basically, that is the meaning of induction, that through the magnetic field, I can induce a voltage in the conductor. Okay? And, well, in particular, this induced voltage is called electromotive force. And also, it is important to take into account that this induced voltage is proportional to the change of rate of the magnetic field and the number of windings. Okay? So basically, let's say that you have like a solenoid, no, you have copper that you have placed in the form of a winding, no, you have designed a winding that has different turns of copper, okay? And based on the number of turns of that copper, you can increase that induced voltage, okay? And also it depends also in the velocity in which I am changing the magnetic field, okay? And here I am wanted to show you like a video demonstration, okay, of what is happening with this law of induction. So in this setup, now this professor is basically using a magnet, okay, and is moving the magnet, okay, inside this conductor. Okay, this is copper, no, this is a coil of copper. And basically we are moving the magnet, okay, in this part in order to induce or generate a voltage in this conductor. And you can see here that he is using here a voltmeter in order to detect this induced voltage when he's moving the magnet. So I will play a little bit about this video. And you can see him here that when he starts moving the magnet, we can see how this indicator of the voltage, no, is moving, or no, this needle is moving from one point and another one. Okay, so let's take 1 minute. No, let's visualize this video for a minute, and you can see how when he's moving the magnet inside this coil, he's basically moving the needle, no, because we are inducing a voltage. Okay, so basically that is the explanation, no, that is the physical demonstration, no, and you can see how he's increasing that voltage when he's increasing the number of copper, the quantity of copper, no, in the coil. Okay, so we are expecting that this bigger coil, and when he's moving the magnet, we will see a greater change in the voltage. Okay, and that effect is basically related to the Faraday's law. Okay, that basically again states that when you move a magnet near a conductor, okay, you can induce a voltage, no? And this voltage is proportional to the rate of change of the magnetic field and also the number of windings or the number of turns in the coil that in which you are inducing that voltage. Okay. So this is one of the laws. The other one is the Ampere's law. And the Ampere's law states that, let's say that you have here a conductor, okay, and you generate a current that flows in this conductor. Well, when the current is flowing through this conductor, that can be any conductor like gold or copper, you are generating a magnetic field that surrounds the conductor, okay? The presence of a current generates a magnetic field, okay, around that conductor, okay? So in this video, but what the person is basically doing, the person of this video is basically connecting gold, no, this is gold, a gold wire, and the gold wire is connected to a voltage source through these cables, through these Cayman red cables. And this, well, when he's turning the voltage, he's generating a current through this conductor. And you will see that in one moment of the video, the orientation of these compasses, no? The orientation of these compasses is changing their orientation because they are being affected by the magnetic field generated by the current that flows through this conductor. So in order to see this, I wanted to show you what is happening, okay? You can see here that when he's turning, he's now turned the voltage source, he's basically changing the orientation of the compasses because the current that flows through this conductor is generating a magnetic field that influences the orientation of the compasses. Okay, so this is one of the important laws also. In fact, the Faraday's law and the Ampere's law are two of the important physics laws that help us to generate or to produce torque via an electric motor. Okay. Also, we have another law that is the Lenz law. Okay, and the Lenz law it's related to the amperes and also the induction law. Here in this diagram, basically means that when you move a magnetic field near a conductor, you are basically inducing a voltage, okay, in this conductor. Let me go back a little bit. You are inducing a voltage, okay, in this conductor, and the voltage also produces a current. And you know that by Ampere's law, this current will generate a magnetic field. But the orientation of the current and also the magnetic field producing this part, okay, has the opposite direction. In fact, here you can see the magnet, and you can see that the lines of the magnetic field are pointing from the north to south pole. But in this case, the orientation of the magnetic field in the right side, that is, this magnetic field is produced by the induced voltage by the magnet in the left side. The magnetic field that is produced in this side is pointing in the opposite direction. Okay, so basically means that when what the Lenz law states is that the magnetic field, okay, induces an electric current in a conductor. And that induced current generates a magnetic field that opposes the change of the original magnetic field. Okay, basically they are pointing in the opposite direction. Since the magnet is moving in this direction, well, the magnetic field will point in the opposite direction. Okay, so when the the magnetic field is moving away from this coil, you will see that the magnetic field will point out in the opposite direction. Okay, you can see that this is pointing up to this side, and the magnetic field of the coil is pointing to the right side. Okay, so basically, no, here is making here another experiment. Now he's moving the magnet away from the coil, and you can see how the magnetic fields are pointing in the opposite direction. Okay, and that is basically related to the Lenz law. Okay, so this is like the demonstration, no? Basically, we are inducing a current that is pointing in the opposite direction of the movement of the magnet, okay? And well, we are basically expressing that information through this sentence, okay? So electric motors, okay? And these are like the three main basic principles, okay? The Lenz law, the Ampere's law, and the Faraday's law, okay? These are like the three main electromagnetic laws that we need to understand in order to see why the electric motor is working as it does, okay? So basically, we are interested in studying the behavior of electric motors because they typically they're the final element in many positional or speed control systems. For example, if you want to control the movement of a robotic arm, if you want to control the movement of a fan, if you want to control the movement of a CNC machine or a 3D printing machine, you need to use an electric motor. Okay, so that's why we are interested in this type of electrical machines, because these electrical machines are typically used in many applications. Okay, and well, for example, the electric vehicles or the hybrid vehicles, their powertrain is based on electric motors. Okay, and well, we can also classify the electric motors into two main types, no? We have DC powered electric motors. That means that we are using a constant voltage source in order to power that electric motor. But also we have AC motors that basically uses a sinusoidal as the input voltage in order to power that type of device, okay? And well, typically, the most important type of motor used in industry is the AC motor. And the reason for that is that AC motors typically provide a higher power, no, a higher torques. And typically, they also provide a greater efficiency compared to DC motors. And also, they don't need a very high maintenance. No, you don't need to make maintenance to these devices constantly. Okay. So, well, there are different types of DC motors. We can classify them in the following way. For example, we have DC motors, we have AC motors, and DC and AC motors can be subclassified into different types. Okay, for example, we have DC motors, and DC motors can be classified between brush and brushless DC motors. And also we can classify more brush DC motors into permanent magnet DC motors, series motors, shunt DC motors, and compound DC motors. Okay. And the reason of having different types of DC motors is that they exhibit different speed and torque relationships. Okay. Typically, in any electric motor, when you increase the speed of the motor, you are reducing the torque. Okay. So the reason of having different, let's say, types of electric motors is that we want to produce different speed and torques relationships. Okay. Or basically, how can we use the electrical components in order to produce different mechanical forces? Okay. On the other hand, we also have AC motors. AC motors can be classified between single and polyphase motors. Single phase basically means that we are only using one voltage source in order to power the motor. Okay. And we can classify them between induction and synchronous AC motors. We will talk about what is the difference later into what is induction and what is synchronous motors. But basically, this difference between induction and synchronous motors is related to the fact that to the difference in speed between the velocity in the stator and the velocity in the rotor of the motor. Okay. Also, we have polyphase motors in which, well, the most common one is a three-phase AC motor. You know? Basically, polyphase or three-phase AC motor means that we are using more than one sinusoidal voltage source in order to power this device. And again, we can classify these polyphase motors into induction and synchronous motors. Okay, so in general, we can understand any motor by analyzing their structure, okay? And these electric motors have two main components, no? We have a fixed part, that means this part is not moving, that is called the stator, okay? That in this diagram, you can see that is basically this cylinder that is outside or that is surrounding the shaft of the motor, okay? This is the stator, no, it's the fixed part of the electric motor, and the rotor is the moving part. In fact, is the element that is rotating constantly and that is coupled with the shaft of the motor. Okay, so the shaft and the rotor are basically coupled together, or typically they are coupled together, and these two elements are the basic structure of any electric motor. Okay, this is another point of view. This is the M view section of the motor. No, and you can see again that here, this is the outside cylinder in which we have the stator, no, the fixed part of the motor, and in the middle we have the rotor. Okay. Also notice that in this section we have the winding, that is basically a coil that is surrounding a core, and the core is typically made of iron. Okay. The reason for that is that if we use iron to produce these windings as the core of these elements, we can produce a better magnetic field. Okay. So this is basically another perspective, okay? Also, it is important to see that we have here a notation that they are telling us that this is the core of the winding that is made of iron, but also we call this as the pole of the motor. Typically, poles are classified in pairs, okay? For example, this is a two-pole um, electric motor because we have one pole here and one pole here, so we have a pair of poles. But also we have another um, pole here and another pole here that form another pair of poles. Okay, so we have one pole here, one pole here, one pole here, and one pole here. And typically we count the number of pair of poles. Okay, and basically the pole is basically a winding, no, within the structure of the stator of the electric motor. And this is another perspective. We have here the shaft of the motor, that is the same part that is here. We have the stator that has the windings, okay? And inside the windings, we have a core of iron that help us to produce a greater magnetic field. And we have the bearings of the motor, you know, that supports the smooth turning of the shaft of the motor. Okay, so again, what is the electric motor? It's basically an electrical machine that converts the electrical power into mechanical power, no? So this is like an animation that in which we can see a permanent magnet DC motor. Basically, we are connecting here a battery to the rotor of this electric motor. Okay, the fixed part is the cylinder, okay, that is surrounding the rotor, that in this case is composed of permanent magnets, okay? And in the rotor, we have this device, okay, that connects this orange device that connects the battery with this contact. And this contact is called a commutator, okay? And this commutator connects the windings in the rotor with the battery, okay? So we have here a lot of windings here. And basically, what we are doing here is that we are applying a voltage to the rotor of the motor. And when we are applying a voltage, we are generating a current. And due to the Ampere's law, this current is generated a magnetic field that is interacting with the magnetic field in the stator. Okay? So basically, the interaction between these two magnetic fields, the magnetic field produced by the current that travels through the rotor through the windings to the windings of the rotor, and the magnetic field in the stator interacts with each other, and the interaction between these magnetic fields produces a torque that allow us to move the shaft of the motor, or in other words, the rotor of this electric motor. Okay, so the principle or the interaction that is helping us to turn electric motors, okay, is basically the interaction between the magnetic fields in the stator and the magnetic fields in the rotor. Okay, there is the interaction, no, of the magnetic field generated in the rotor and the magnetic field generated in the stator. Okay, and that interaction is helping us to move or to produce a torque that moves this rotor and also moves the shaft of the motor. And well, this is like a general overview, of what is a DC motor. But as I told you, we can classify DC motors into two main elements, no? We have the brush and brushless DC motors. In particular, the main difference between brush and brushless DC motors is the way in which they are commutated, okay? In this case, for the case of the brush motor, that is the same one as the animation that I shown previously, you have in the stator, you have a magnetic field that is fixed that can be produced by a magnet or a winding, okay? But in order to make this, to provide power to the rotor, in order to start turning, we need to use a commutator, okay? And this commutator basically controls the flow of current in the windings in the rotor, okay? And by doing that, by using this commutator, we can produce torque continuously inside the machine, okay? But in the case of the brushless motor, what we are doing is to place windings, okay, in the stator, no, as you can see here, these are windings, no, these green cables are windings with their respective core. But at the center, that is where the rotor is placed, we are placing a permanent magnet, okay? So that is the main difference in architecture, that in the rotor, instead of using a winding, we are using a magnet, okay? And also, another difference is that the commutation is performed electrically. In other words, we are controlling the activation of these solenoids or these electromagnets that are placed in the stator in a way that we can produce a varying magnetic field that surrounds the rotor that surrounds the permanent magnet in the rotor. Okay. And this varying magnetic field that we can control by activating or deactivating the windings in the stator produces a torque. Okay, but we are controlling the generation of this magnetic field in the stator. Okay. And we need to switch, no, we need to perform an electronic switching of the solenoids by using transistors. Okay, so we need to, and also in a way we are based on a DC voltage, we are generating an AC voltage, okay, through the electronics. Okay, it's very similar, for example, to like the process that an inverter in an electric vehicle it does, because it converts the DC electrical energy into AC electrical energy. And we are doing a very similar process by generating this magnetic field that surrounds that is producing the stator that is basically moving around the rotor, okay? So the main difference between the brush motor and the brushless motor is that here the commutation is mechanical. Basically, we are disconnecting the contact between the battery and the windings in the rotor, okay? And here in the brushless motor, the commutation is electrically controlled, and we are using solenoids to control the commutation and the presence of the magnetic field in the stator. And also, instead of using windings in the rotor, we are using a permanent magnet, okay? And the main difference or the main advantage of this architecture of the brushless motor is that the brushless motor is more efficient compared to the brush motor, okay? So here are some comparisons. For example, in the left side, there are some characteristics of brush motors. First, we need high maintenance for brush motors. Also, they have low efficiency. They are easy to control. No, that is their main advantage. We can control them very easily. But the problem is that they require mechanical computation. That is also related to the fact that they require high maintenance. On the other hand, we have the brush motor, in which we require a lower maintenance. They have a higher efficiency, but the problem is the control, because we need to control the activation or disactivation of these solenoids, okay, or these windings, in order to produce a varying magnetic field or a rotative magnetic field that interacts with the magnetic field of the magnets in the rotor. So basically it means that we need to perform like a DC to AC conversion. And what the reason that we have a low maintenance is that the commutation, okay, required to make this rotor turn is that it is electronic, it is not mechanical, okay? So that is the main differences between these two types of DC motors. This is another diagram, okay, in which again you can see that we have the commutator. Here we have windings connected to the rotor. And basically, when we are applying a voltage to this cable, we are generating a current that produces a magnetic field that surrounds the trajectory of the current. And this magnetic field produced by the current interacts with the poles or the magnetic field in the stator. Okay. Typically, also we call this part, no, the rotor, the armature of the motor. Also, what we can place instead of magnets, windings in order to produce a fixed magnetic field in the stator. And well, also remember that we label these windings in the stator as poles. Okay, there are poles that basically produce like this north and south pole that allow us to produce a magnetic field in the stator in order to control the turns of the motor. Okay. And well, we have different types of DC motors, as I mentioned previously. We have permanent magnet DC motors, we have series motors, shunt DC motors, and compound motors. Okay, the most common one, or one of the most common ones, is the permanent magnet synchronous motors. That is very similar to the architecture that we saw previously, in which we have permanent magnets in the stator, and in the rotor we have windings. Okay. And we have again the commutator that is connecting the battery through the windings that connects the battery of the motor with the windings in the rotor. Okay. And basically the characteristics of this permanent magnet DC motor is that we are placing magnets in the stator. Okay. And one of their advantages is that they are very simple in construction and they are typically used as starters of automobiles, washers, and also toys. And again, well, here you can see that we have again the permanent magnet synchronous motor. Again, this is the stator, this is the rotor, this is the shaft of the rotor. Here we have a commutator. These are the brushes, no, that connect the battery with the rotor. Okay, these are basically contacts. And well, here we are saying that this is a two-pole DC motor because we have one winding here, okay? And also we have another another pole here. No, this can be the north pole, and this can be the south pole. Okay. And well, by considering this, and if we want to analyze these electric DC motors, we typically can use the following circuit, in which we have a resistance, okay? This resistance basically represents the electrical resistance of the cables in the rotor, no? These windings in the rotor. Also, these coils or these windings can be understood as inductors, okay? That's why we are placing this symbol for the inductance, okay? That has a value of L, okay? And also we have here a very particular element that is called the voltage V sub B. And this voltage V sub B basically stands for the back electromotive force. Okay, so what is the meaning of this? So let's go back a little bit. If you remember, we are connecting here the battery is connected to the windings in the rotor, and when we're connecting a battery to these windings, we can produce a current, and the current produces a magnetic field that interacts with the magnetic field in the stator and produces a torque. Okay, but also remember that due to the Faraday's law, here we are moving a conductor inside a varying magnetic field. Okay, this conductor is in presence of a varying magnetic field that is present in the stator of the motor. So if you remember the Faraday's law, remember that the Faraday's law states that if you put a conductor near a magnet, you can induce a voltage. Okay, so this means that the conductors that we have here in the rotor are being induced by a voltage due to the presence of this magnetic field in the stator. We are inducing a voltage because we are placing these conductors inside a magnetic field or near a magnetic field that is also changing, okay, because it is rotating, okay. So the reason for why we have this voltage is to model this back electromotive force or back EMF that basically considers the voltage that is induced by the magnetic field of the stator. Okay. In fact, this is a circuit that represents the electrical behavior of the rotor because we have the resistance of the windings in the rotor, the inductance of the windings in the rotor, and also we are considering the voltage induced by the magnetic field uh, of the stator, okay? And this is basically the voltage that we are applying to the rotor, okay? And well, in fact, well, you can define the back EMF voltage as a constant of the motor, no, a constant for the back EMF of the motor, and also this phi is related to the magnetic flux of the permanent magnets or the flux of the magnetic field in the stator. And here we have the speed of the motor, no, in radians over second. So basically, this means that the back EMF is dependent on the velocity of the motor and also the magnetic flux of the magnets or the magnetic field and also the back EMF constant of the motor. So these are characteristics or properties of the motor that you are using. But at the end, basically this relationship states that this back EMF depends of a constant and the velocity of the motor. And this constant depends on the magnetic flux, okay? Or the magnetic field of the produced by the stator, no? Okay. So another way to simplify this is to say, okay, we are applying a voltage, and here we are considering two elements, the back EMF voltage, denoted by the letter E sub B, and also we have a resistance in the armature, okay? And that remember that the armature is basically the connections, no, in the rotor of the electric motor. Okay, well, notice here that we are getting rid of the inductance, no? Remember that from the AC circuit class, we discussed a little bit about that these elements have certain the resistance that depends on frequency. But here you can observe that we are getting rid of that because the impedance of an inductor in DC, or where we don't have a frequency, no? In DC, we can say that omega is equal to 0. So the impedance of this element can be discarded, and we can represent the presence of this inductor with a cable. Okay. So this is like another way to simplify the analysis. Basically, we have the voltage applied to the rotor. We have the armature resistance, that is the resistance in the windings of the rotor. And also we have the back EMF. Okay, voltage induced by the stator due to the magnetic field producing the stator into the windings or the conductors placed in the rotor. And well, we can also, well, for these circuits, we can generate this relationship between torque and speed. The important part of this diagram is that you can notice that for any electric motor, if you increase the speed of the motor, you are producing a lower torque. Okay, basically these lines show the relationship between the speed of the motor and the torque for different voltages. But in general, you can observe that as you increase the speed of the motor, you are also decreasing the torque. Okay, or if you decrease the speed of the motor, you are gaining more torque. Okay, and we can use, for example, this relationship to compute the torque, okay, produced by the motor, okay? Also, you can use this expression, no? That is basically the torques is dependent to the constant of the motor that also is related to the magnetic flux of the motor times the current. Okay, so if you take the current and these constants, you can compute the torque that is produced by the electric motor. Okay, and well, if you remember, I said previously that we can have different types of electric motors. Basically, the diagram is essentially the same because you can see that we have the voltage and we have the back EMF voltage and looped together with the armature resistance. But sometimes they are placing like this winding in parallel with the armature, and also you have another winding in parallel with the armature. And also we have this winding that is in series with the armature of the motor. Okay. But these different configurations, what they're basically trying to do is to produce different speed and torque relationships. Okay. So for example, for a series motors, you can see how the speed decreases. Well, as you increase the speed, the torque is decreasing. For a shunt motor, you can see that if you use this type of configuration, you can obtain this behavior in which you are basically uh, changing a lot the torque of the motor, but the speed barely changes. Okay, the change in the speed is less pronounced compared to the series motor. Okay, and the compound motor is basically a combination between the shunt and the series motor. Okay, in fact, you can see that we are placing this shunt field in parallel with the armature, and also we are using this shunt field in series with the armature. Okay, so it's like a combination of the series and shunt motor. And the idea is to have a speed and torque relationship that combines the two behaviors. Okay, and um, well, and these are like the important equations. We will be using these equations later on during the class. But the important part here is that if you want to compute what is the power that the electric motor can deliver, you can use the compute. You need to compute what we call the electromagnetic torque of the motor times the velocity of the motor. Okay, in radians over second. And also you can compute this electromagnetic torque based on the constants of the motor times the current in the armature of the motor, okay? So you can use this relationship to compute the electromagnetic torque, and you can use this relationship to compute the mechanical power produced by an electric motor in the DC domain. And also, you can compute the mechanical power produced by the motor if you consider the back EMF voltage, okay? This voltage stands for the back electromotive force times the current in the armature, okay? So these are like the three important equations that you can consider because later we will be using these equations to solve some exercises, okay, related to DC motors. And well, what else? Well, also another aspect that I want to, you can take a photo of this. I will upload the presentation later. But the important thing that I want to also discuss with you is how you can control DC motors. Okay. Well, that will be the topic of another video. Okay, so see you later. Mm, mm.